the last section of Unit 4, we've been looking at free fall and projectile motion. So in this section, we're going to take a look at what happens when you have a projectile that is actually given an initial angle. So as we've been talking about, when we've talked about projectiles, we've had projectiles that are just dropped. We've had things that are thrown with some kind of an initial either up or down component to the velocity. And then the last section, we looked at what happens if there's a horizontal component to the velocity, but not a vertical one. So in this section, we're going to take a look and see what happens when you have both a horizontal and a vertical component to the initial velocity for a projectile. So as we look at this, the first thing that we have to understand is what happens when you have a vector that is at an angle and how do you deal with it. So when we've talked about vectors in the past, we've just said a vector is something that has a magnitude and a direction. So those can be physically represented with arrows. So here we have an arrow and that gives us kind of a basic direction, and we have a magnitude of the 45 meters per second. So the length is the magnitude. The angle there is going to help indicate the direction and the tip as well. So if I want to describe this vector in just a short number statement, I can say that this is a vector that is 45 meters per second at a 30-degree angle. Now in math, sometimes they use the full circle, 360 degrees, to describe the direction of the vector. That's super convenient. What our curriculum does instead is it actually uses compass directions, which is also very common. So in this case, you can see that this vector has a little bit of a north to it and a little bit of an east to it. So the way that I write this using compass directions is I'm going to say that this vector is 45 meters per second at 30 degrees, because that's really specific. And if this is east, it's going to be 30 degrees north of east. So that's how my vector is written, 45 meters per second at 30 degrees north of the east. So here's my east, it's north of it. The other way that you could write this same vector, if you used the 60 degrees, which would be off of the y-axis, that could also be done. You could say it's 60 degrees east of north. So north would be your y-axis, it would be east of it, 60 degrees. So those are two ways to write the same vector. So typically what you're doing in projectiles with vectors is that you're going to need to break them down, or they call that resolving. We're going to resolve them into x and y components using trig. Now some of you guys have had trig more recently than others. We only do basic right angle trig in this class, so you may need to do a little bit of a review, but it's not going to get too detailed in this class, the kind of trig that we do. So if I want to find the x component for this triangle, I know that I have the hypotenuse and I have an angle, and that this x would be adjacent to this angle, where the y would be opposite the angle. So when we talk about trig functions, we're going to say the cosine is the adjacent over the hypotenuse. So since I'm looking for x here, I'm going to say the cosine of 40 is the adjacent x over the hypotenuse of 80. So when I do that out, I'm going to find x, in this case, is 61 miles. Now, if you want to make that a little quicker for yourself and not have to write out a full adjacent over hypotenuse every time, that can be simplified into a little shortcut. It's typical because since we're doing specifically projectiles, you can say that you're going to end up with the same rearrangement of the equation every time. So you can say the x component is the hypotenuse times the cosine of theta. That always works as long as the angle's from the x-axis, which is typically how it's given. But if they gave you 50 degrees here, then you couldn't use this shortcut unless you subtracted the 90 minus 50 to get the 40. So if you have the angle off the x-axis, you can always find the x component of a projectile by doing x equals hypotenuse cosine theta. So we're going to do the same thing and find the y component. So the y component is going to be opposite over hypotenuse. So my opposite is going to be here, and my hypotenuse is 80. So if I do the sine of 40 as y over 80 and I solve that, I get a y of 51. So same thing here. As long as the angle is taken from the x-axis, then you can use this shortcut and say that the y component is hypotenuse sine theta. By the way, as you do these, especially if you're in a math class that is using radians, you're going to have to remember to switch back to degree mode for physics. And that can be a little bit annoying, but it's really important. We don't do radians in this class, so you need to be in degree mode anytime that we do angles in physics. So here's some basic vector addition. This is something that is really common in physics and something that you need to be comfortable with in this section. So if you're going to take two vectors and add them together, the rule is you have to add them tip to tail. So I'm going to draw arrows to represent my vectors again, and on those I have a tip and a tail. So what I'm going to have for this first example is I have 50 meters east. So my east is my direction, so I'm going to draw this to the right. So this is my tip. That means my next vector must be drawn here. I can't just attach it anywhere to this arrow. It has to be tip to tail. So I'm going to draw in what's called the resultant. The resultant is basically the answer. When you draw the resultant, you start where the original vector started and end where the final vector ends. So in this case, it's going to look like this. And you can see pretty easily visually that that's going to be 70 meters east. If you haven't yet, you will do these in math, and you'll do them a whole lot harder in math. We just do some basic stuff in this class, but it'll get you started. So on example 2, I have 40 meters to the east, and I'm going to add 60 meters west. So in this case, I have two different directions. So instead of, it's important to know where to start your next arrow. So I'm going to go tip to tail again. So here's my tip and here's my tail. So I can't just put this tail to tail. I couldn't move this whole arrow and have it up here. That wouldn't make any sense. So I have to go tip to tail. So my resultant starts where my first vector started and ends where my last vector ends. You could add more than two vectors. There's no limit to the number of vectors that you add, but we probably won't do any more than two. So here's where my first vector starts, where my last vector ends. And then you can see that what's left over between these two is 20 meters, and it's going to be pointing west. So easy enough to do straight ones. It's more interesting and more applicable to this chapter in physics to do some that end up being a triangle. So here we have 60 meters west, and I'm going to add 20 meters north. Here's my tip to tail, meaning this vertical arrow here, the 20 meters north, I do not put it over here because I have a tip and I have a tail. That's where they have to match up. And then my green resultant starts where the first vector starts, ends where the last one ends. So I'm going to follow that rule. So what I need to do then is to find the value for that third side is I'm going to use the Pythagorean theorem. And when I do that, I find that the third green side is 63 meters. And I'm going to look at my triangle and say, okay, that makes sense because it should be bigger than either of the other two sides. Always try to remember to go back and make sure your answers make sense. So now we're going to find the angle. You could really use any of the two out of three sides that you would like. I went ahead and because the 63 may be rounded, I'm going to go ahead and use the 20 and the 60 because I know them exactly since they were given in the problem. So if I want to find this angle, and this is the one that you want to look for because this is where the resultant starts. I don't care about this angle, that's where it ends. I want to know what direction is the resultant from where it started. So I'm going to look at this angle and do 20 is my opposite and 60 is my adjacent. So opposite over adjacent is tangent. In this case, I'm not given the angle and I want to find the angle. So I use the inverse tangent button on my calculator. When I do that, I'm going to find an angle of 18 degrees. Now, if you ever get like a crazy looking number, first thing is check and make sure you are correctly in degree mode on your calculator. Okay, so this would be my answer, 63 meters at 18 degrees, and now I'm going to add that compass direction. Since the 18 degrees is actually off of what would be the west direction on a compass, it is 18 degrees north of west, and that would be the solution for this problem. So how that applies to projectiles in free fall, because that's really what we're talking about in this section, is we're going to do the similar kind of a thing, but we're going to apply some physics numbers to it instead of just looking at arrows. So let's say we have a football kicked with an initial velocity of 25 meters per second at an angle of 45 degrees with the horizontal. Determine the range of the ball. So the range is the horizontal distance traveled. That's what I'm going to look at. So here's my overall strategy. I'm going to again break the velocity. I'm going to break all of the variables up into x and y components, but specifically the thing that's different than the last section is I have to break that velocity into x and y components. So I'll do that, then we'll find the time it takes, and then we'll use the time from the y direction in the x direction to solve for the range. So here's an assumption you have to make. They don't tell you how high like the ball was off the ground when he kicked it, so you kind of just have to assume that the ball ends at the same height it started at. You can say it ends that you must have started on the ground, but if they don't give you any way to account for that, you just have to assume that its ending height and its starting height are the same. So here we have a football kicked with an initial velocity 25 meters per second. So in my y direction, I'm going to take that 25 meters per second and I want to find the y component of it. So I'm going to do hypotenuse sine 45. That's the shortcut that we looked at earlier. Hypotenuse sine theta gives me the y component. So out of the 25 meters per second, 17.7 meters per second of it was in the y direction. Now, if it's going to end up at the same height, I can say that final velocity is going to be the same value, the 17.7, but with the opposite sign. And then, oh, that looks like that's hidden a little bit on that one. So we don't know we know that the height is going to be the same as that it ended with, so I'm going to have an x equals 0 there. Okay, so I'm going to go ahead and use my who cares for x since they didn't actually ask us about it. You can say that it's 0, but we know it's going to be in free fall, so it's going to have an acceleration of 9.8. So I will put my numbers in using that. Again, I could have used a different equation. You could have used one with x in it if you wanted to. And then you find the time. Again, here, if the time turns out negative, go back and check your answers, your numbers, to make sure that your signs all agree with each other. So let's take a look in the x direction. Same thing in the x direction. I have to figure out how much of that 25 is in the x. We already said how much was in the y. Now, interestingly, in this case, because it's a 45-degree angle, the sine and cosine of that are actually going to end up being the same value. If it were any other angle, they would not be the same. So my shortcut here is going to be hypotenuse cosine theta. Again, that works as long as the angle is off of the x-axis. So we want to find the range of the ball, and we just figured out how long it was going to take before it landed. So I'm going to use my constant velocity equation here, x equals vt, and solve for the range of the ball, how far away from the ball in the x direction that it landed. So that's how you do a basic projectile problem. So most of the problems are pretty much like that. You do again have to watch your signs, particularly if something has an initial velocity that's down. I think that can be a little bit confusing. But here's our main ideas for this whole section. When you're doing vector addition, you have to add tip to tail. Anything that's a vector has a magnitude and a direction. Our curriculum uses the compass notation for that, so be careful of using that. Projectiles launched at angles have to be resolved into x and y components. Time is the same in each direction. So you're going to use that same problem solving strategy we did last time with the horizontal projectiles. You solve for time first, and then you'll solve for whatever the required variable is. So that's how projectile problems work when the projectile is fired at an angle. And that's going to be the end of this section.